Hey guys, today we're going to look at a summary of normal distribution. It could be one of three summaries, but at any rate, they might overlap, and if they do, that's great for review, and if not, that's good too. Uh, so first of all, um, normal distribution, this is very important in statistics. Keep in mind, a z-score gives an indication of how unusual a value is because it tells you how far it is away from the mean. Going back to the central limit theorem, 68% of your data is one standard deviation above or below the mean. If it's 95%, then you have 95% of your data is two standard deviations above or below the mean. And 99.7% of all your data is within three standard deviations above and below the mean. In a normal distribution, drawing it up, you got that nice looking bell curve, or bell-shaped curve. That's a normal model. We call it symmetric. The area under the curve, as you can see in this picture, it should equal 1. The total area is 1. Even though the ends of the bell curve never reach the x-axis, it gets very close. Right in the middle is where the mean is located, mu. My daughter likes to call it moo. She's only 2. Properties of normal distribution. Mean, median, mode are equal. The normal curve, like we mentioned before, is bell-shaped and equal to the mean. There's some few key points that a couple of them I've already talked about. The points at which the curves change from upward to downward are called the inflection points. Here's kind of an example, interpreting a graph. The heights of fully grown white oak trees are normally distributed. The curve represents the distribution. The mean of the fully grown oak tree, the mu is 90, and we have some inflection points, 3.5. Okay. So when we look at a bell curve, we can actually understand the mean and the standard deviation. Which curve has the greatest standard deviation? Curve B has a greater standard deviation because it is more spread out than curve A. Curve A is a little bit more focused around a smaller range, if you will. What we'll do next is go over a few examples, understanding what happens when you standardize data. So I will see you here in just a second. That was the longest second of my life. No, just joking, really. Let's take a look at just standardizing, some data. I want you to see some things that I find really interesting. Let's look at this formula here. I use x minus mu. I can't make a mu symbol. I could draw a cow, but yeah. I'm going to go ahead and just give you some IQ, give you an IQ test score. Let's say we have an IQ test score of 110. And the population means 100. and the standard deviation is 15. It's kind of like the standard example. um, what happens is when you standardize a score, I don't want to say you're almost shifting or transforming the mu. And let me go in a different color. You're transforming it as when you standardize it, it's going to end up being 0, and the standard deviation will end up being 1. That's after you standardize your data, and you kind of end up with the same thing. So, let's just try this. I'm going to change different colors here, just for example. If we want to standardize a value and find a z-score, let's go ahead and do that. We're just going to plug and chug here. 110 minus 100 over our standard deviation is 15. That's going to give us a z-score. All right. With our IQ test score being above the mean, we should end up with a positive z-score. We have 110 minus 100, which is 10. Then you can do 10 divided by 15. Which is, 0.666. We'll just go 0.67. So that we're not being too evil here. So that's our z-score, and it's 0.67 standard deviations above the mean. So what happens is, guys, is that since I standardized this score as 0.67, okay, that made my mu 0 and my standard deviation 1. I'm going to draw my little fancy little bell curve here. Here's mu, obviously. And standard deviation is 1. We got my z-score right here is 0.67. So I'm looking about right in there. Maybe not. It's not terribly good or bad either way, but you get the idea. It is above the mean, to the right of the mean. If I wanted to find the area to the left, the probability of getting that score, okay, that goes back to reading the Z chart. You can just look up 0.67, but I'm going to show you an even easier way. I'm just going to go straight to my TI-83, which is down here. And what we'll do is we will go to second vars, and we're going to run a normal CDF here, okay? Now, since we're looking to the left, notice I put -1 E99, and the upper is actually going to be my z-score, because you're setting a boundary anyway, all the way to the left, infinity, all the way up into 0.67. So I'll go 0.67. After we standardize, our mu is 0 and our standard deviation is 1. So let's go ahead and go down to paste, click on paste, and then hit enter. So what we have here is a 0.7485 probability. I'm going to minimize that, 0.7485. So that's my probability. I almost couldn't talk. Or if we want to go percentages, times that by 100, you get 74.85%. So if you go back and think about this, to score a 110, I'm going to highlight that. To score 110, we have a 75% chance of scoring a 110 or below. All right. Now, I want to go back to this graphing calculator for a second. See what happens here. If you're using the graphing calculator, which I like, let's do another normal CDF. You just go second vars. Okay, normal CDF here. I could just hit 2. All right. These are boundaries. All right. If we look at changing the upper to, what was our score again? 110. Right. Now our mean was 100 and our standard deviation was 15. Watch what happens here. Paste again, blah, blah, blah. Okay, pretty much you get the same thing. All right, so you still have that 74.75, 74%, 75% chance of scoring between a 0 or 110. So I find that interesting. When you standardize a score, you know, it wasn't really exact what we wrote for our percentage here, but nonetheless, it gets pretty close. Now, one more example I'd like to do before I get off here. Let's say we want to find the probability of scoring between, now this is going to be a two-tail situation. What's the probability of scoring between an 80, I'm in highlight mode, 80, okay, and 120, okay? So if we were taking this IQ test, which I'm almost afraid to at this point, to score between these two values, and we still have a population mean of 100, a standard deviation of 15, okay? Now what happens is you can go the long way around it and standardize each one of these and then subtract and find a difference. With the graphing calculator, going under that normal distribution, or I'm sorry, normal CDF, I'm going to clear this, get rid of that malarkey. I can actually just punch in those numbers just in the exact same order. Okay, think about this. Okay, you have a lower bound. Okay, normal CDF. I'll just kind of write it down here. You have a lower bound, which is 80, comma, and then our upper bound 120, and then you just punch in your mean and standard deviation, and that will give us the probability of scoring between an 80 and 120 without having to go through and use and standardize 80 and 120, find a difference and all that. So the graphic calculator is just genius. So we'll punch in our boundary. Let's put our lower limit, which is 80, and our upper limit is 120. Okay, everything else looks good, so I'm going to go down, paste, and got to hit enter again. So right there is our probability of scoring between an 80 and 120. As a percentage, just times that by 100, we get 81.75%. And that's all she wrote. So hopefully this gives you a general idea of how to use a calculator and calculating the probability using a normal model. And then the relationship between the z-score, you know, when you standardize scores, you know, what happens to the mean and the standard deviation. well, after you standardize the score, the mean becomes 0, and the standard deviation becomes 1. So hopefully this video kind of helps shed some light on some issues you may be having. And until next time, take care of yourself. Later on.